One of the things that you'll quickly learn in calculus is that there's really nothing magical about the x direction. We often think of integrals as always ending with dx, but actually, there's nothing special about that. You can integrate in the y direction using the variable, sorry, using the differential dy at the end. So uh, when we're finding area between curves, it's actually sometimes easier to do to find an area in this way. So what we're doing when we find an area in the y direction is instead of adding up skinny rectangles whose width is dx, we're really adding up very short rectangles whose height is dy. We're going from a horizontal line at the bottom of y equals a up to a horizontal line at the top of y equals b, and we're just adding up, we're stacking up rectangles whose height is dy. As you can see in the case of finding the green region, that's what we're doing, and I've drawn in one representative rectangle. So what happens is the paradigm completely reverses. Instead of integrating from the left to the right and finding a rectangle where we know the top function and the bottom function, instead now we're integrating from the bottom up to the top, and we're finding a rectangle whose height is, not whose height, whose width actually, is given by the left function, sorry, the right function minus the left function. So here we have the right function is x equals f of y, and the left function is x equals g of y. So the width of this rectangle is going to be, sorry, it's going to be f of y minus g of y. So the area of this green region, so we're going to see this is the integral from a to b, but now this refers to y equals a and y equals b. And then we're going to integrate left minus right, so this is going to be f of y minus g of y dy. So in this case, this is the left, sorry, this is the right, this is the left, and so this is now the width of the rectangle, this is its height, and that's the area of one typical rectangle. Okay, so sometimes it's easier to do this because, as you can see, in this case, what we have is we actually have two curves that are not functions of x. So they would in fact fail what you know is the vertical line test. The vertical line would intersect these curves in more than one place, so it's not really even possible to write these as functions of x, except maybe for if you break it up in some way. So this is an example of a situation where it would be easier to integrate in the y direction. Let's turn to a problem. So let's find the area between these two curves, x equals y squared minus 1, which is the purple curve, and x equals y squared minus 1/8 y to the fourth plus 1, which is the green curve. And you can probably see the problem if you tried to integrate this in the x direction. You'd have to find which is the top function, which is the bottom function, but it's actually not all that clear. Is if you look at, let's say, this line right here, you can see that the vertical line intersects these two curves several times, and if I had to say which one is on top, which one is on bottom, is it the purple or the green, it switches at the same point. There's just no way to there's just no way to treat that as uh, there's no way to treat that using the top minus bottom paradigm. So what we're going to do is we're going to integrate this in the y direction to find the area. First thing we need to do is find the points of intersection. We do that, it's the same as what we did before, except now we're going to set the y parts of these equations equal to each other. Keep in mind that what we're doing now is uh, instead of integrating y as a function of x, we're going to be integrating x as a function of y. So you expect to see curves written sort of in this form, x equals some function of y. We set this up this way. We're going to write y squared minus 1 equals y squared minus 1/8 y to the fourth plus 1. And now I'm just going to zip through a whole bunch of algebra. So we see that these two curves intersect where y is equal to either positive 2 or negative 2. So I'm going to write those in here. So that's going to be positive 2, and that's going to be negative 2. So those are actually going to be, those are going to give us our limits of integration when we integrate in the y direction, because we're integrating from this line down here all the way up to this line. Okay, so we can now see which ones are the right and left curves. The curve on the right is the green one, and the curve on the left is the purple one. So through the magic of television, I've been brought to a new screen where there's a small diagram of the same region. So let's set this up. We've already determined what the upper and lower boundaries are, as well as what the right and left curves are. So we're going to write the area is equal to the integral. Remember, I go from a low y value of -2 up to a high y value of +2, and then I integrate right minus left. The right curve is y squared minus 1/8 y to the fourth plus 1, and the left curve is y squared minus 1, and I integrate that in the y direction. And now I'm just going to zip through the algebra. So there's the answer, 32/5. So now it's your turn. Take a look at this diagram and follow the question to set up the correct integral in the y direction to give the area of the yellow region. And by the way, hint, the line x equals 3 can be a right or left boundary.